So now last video we start to prove this big theorem that being positive definite means has many equivalent definitions. So two of them being when you integrate against the convolution of f against the involution of f, or you integrate against a measure convolute with the involution of the same measure, you have something greater than or equal to 0. Okay. So we almost proved these equivalence, and we actually only left one direction, which is 4 implies 5. So let me just remind you, 4 basically means if you integrate against some compactly supported functions, then you do the double integral of fxy inverse, and you integrate against 5xy inverse, you get something that's non-negative. 5 being you integrate against the lambda conjugate with lambda involution, you have something non-negative. All right, so the proof of this is slightly technical, and we actually require slightly some development on the convolution between a function and a measure. Okay, so let's get this started. All right, so now let's just want to prove 5. So basically, I take any lambda inside the M of G. Okay. One thing about the M of G is, again, because your lambda being a bounded random measure, so you can find something that's compactly supported. Okay, so there exists a lambda n inside the M of G, where your lambda n, each of the support of the lambda n is compact, and your lambda n is going to converge in lambda in the corresponding topology. Okay, so as in the you treat them as the dual of the C0 function. So it's the weak star topology there. All right. So basically now what we have is that for every function f, I want to define a convolution with this fn or this lambda n, and also lambda. Okay, so now I want to develop this idea. So suppose I have a f inside CC of G, okay, and then let's just take lambda inside M of G for now, okay. So you can treat your f as a CC of G, or in L1 of G, you can treat it as ff dx inside the M of G. So you kind of have a convolution of these two measures. I just want to briefly talk about what they look like. So if I consider the integral of a function g inside the L1 space, and you do the convolution of this measure. So let's maybe give it a name. So let's call it maybe mu of f. Okay, let's just call it for now. And so you have this mu f. You convolute with this other measure called lambda. All right. So by definition, this is just the double integral of g of xy. You do the xy, you give it to the first one, so lambda f of x, and the y goes to the second one, lambda of y. And what you can do is that, well, the mu f is just equals to f dx. So this is the double integral of the gxy f of x dx and d lambda y. And now because your x is the left invariant Haar measure, so you can use the left invariance to translate this xy. So here the y is fixed. So given a fixed y, you translate the x by y inverse. Okay, so this is, we have seen this trick multiple times. So now this one becomes the integral of gx of the xy f of xy inverse dx and d lambda y. All right. So now you can just rewrite this as the integral of the g against, well, multiply by the following. So you integrate, so let's say g of x here, you integrate the f of xy inverse, and then you do the d lambda y, okay, and this whole thing dx, all right? Well, the good thing is that now basically on the left-hand side, I'm just writing integral. So I integrate this measure against any L1 function, and it's the same as integrating this g of x against this new measure. Okay, so if you compare these two, by the representation, they have to be the same measure. Okay, so in other words, this in particular, you may notice that, well, this convolution of the measure mu f with this lambda it looks like the convolution, well, it looks like a measure of some function dx. Okay, so let's give that function name. So let's use the notation that f convolute with a measure lambda, evaluate at a point x to be this integral. Okay, so this is the integral of x y inverse, and then you have a d lambda y. Okay, of course, if your lambda is also some L1 function times dx, then this is just your usual function convolution. Okay, but in general, your lambda can be just some measure in the measure space. Well, but one thing you notice immediately is that this one is in the L1 space. Okay, so your the integral of your f convolute lambda dx. Okay, fx, the absolute value dx. All right, so this is just equals to the double integral, or let's just say less than equals to the double integral of the f of xy inverse. You do the d lambda y first, and then you do the dx. All right, but because you integrate, when you integrate against the dx, you use the left invariance and so on. So this is less than equals to the integral of the one norm of f d lambda. And then because your lambda is inside the m of g, this is bounded above by the one norm times the norm of your measure lambda. Okay. So this is going to be bounded. So you have a L1 function again. Okay, this is it really looks like a convolution of the convolution on your measure space is a Banach algebra. So you do have this kind of inequality, but in particular, now you convolute a function with a measure, you get an L1 function. Okay, so that's really nice. And in fact, this is also compactly supported if your f and lambda are compactly supported. So let's say if the support of f and your support of the lambda are compact, then you have something compactly supported. The reason is the following. So all right. So this is kind of tricky because this convolution is basically integrating over this f of xy inverse. So to have this integral to be non-zero, your xy inverse has to be nice enough. Okay, so if x is too far away from the product of these two support, then your integral has to be zero. Okay, and I also want to show that this one is not only in L1, but it's actually also continuous. Okay, so why is it continuous? Well, if I want to evaluate this, say x1 minus the convolution at x2, all right, so by definition, this is going to be, well, less than equals to, I move the absolute value inside, so I have the f of x1 y inverse minus the f of x2 y inverse, the lambda of y. Okay, so this is the definition. And because your function is continuous and the support of the lambda is compact, so this one, well, f is going to be uniform continuous on the support of the lambda. So this one can be bounded above by some epsilon, as long as your x1 and x2 are close enough. And because your lambda is also bounded, so this whole thing is going to go to zero as x1 close to x2. Okay, so this is really just follows from the continuity of the f and the compact support of lambda. So what we have is that f convolute with lambda. This is a continuous function. Okay. So because it's continuous, so it's also compactly supported, so it's in CC of G. So in other words, this is in CC of G again. Okay. So if you convolute a CC of G with any measure, you again land back in CC of G. Okay. Of course, the M of G the lambda has to have compact support. All right. So now I want to show that. Well, now you have some lambda. You want to show that the integral of phi against the lambda convolute with the lambda check, that's going to be positive. Okay, so let's do it when lambda is actually just compactly supported because you can always use compactly supported lambda to approximate your lambda, okay? So what you can do is that, well, you can think about these convolution against the f, okay? So if I compare it with the integral of phi of the f convolute with lambda, and then I convolute with the involution of these again, and you know the involution by the property of the involution, this is involute against lambda check and the f check, okay? So this one, because I have something inside the CC of G now, okay, so f is inside CC of G, so this whole thing by 4, this is going to be greater than or equal to 0, okay, this is by 4, okay? So now I can expand this by the following. So this is going to be super ugly, but in fact, I have well, 4 integrals, okay? So it's just 4 measures convolute together, okay? So you know how to convolute 2, so you know how to convolute 4. I'm just going to write what it looks like. Essentially, you break 4 things, a product of 4 things respect to your measures. So you have x, y, z, the last one, let's say t, and then you plug in x, y, z, t to the corresponding measure, okay? So for the f, it's just fx. For the lambda is the lambda of y, and then let's just do the f first. So the first and the last are for the f, okay, or f check. And so this is dx dt. And then you have a d lambda of y, and then you have a d lambda check of z, okay? So they have to be the same, okay? This is just the formula. All right, so now suppose I can pick my function f with some compact support, and we can make it support on smaller and smaller sets, okay? So let's say pick f so that first of all, the integral of f is going to be equals to 1, and the support of f is really close to the identity, okay? So we can always do that, okay? And because your phi is going to be continuous, okay? So phi is a continuous. So if I look at the inner integral here, so the integrate against the f and x and t, because my phi is continuous, in fact, uniform continuous, so and it's only non-zero on the support of f, okay? So you can see that this can be approximated by when x and t are essentially just equals to the identity, okay, by the continuity. So I'm kind of doing something not too rigorous, you can fill in the detail, but this one is approximated by the f of yz, okay? So on the support of f, okay, support of f, okay. All right, so essentially this, if I say this is the star, okay, then the star, we know that's bigger than 0, okay, that's by number 4. So star is approximately equals to the double integral where I replace the inner double integral by phi of yz, and then I have d of lambda y and d of lambda check of z. And this is essentially just equals to the integral phi against the d lambda convolute with the involution lambda, okay? So this one is also positive, okay, because they have to be close together. All right, so now just use the extended from lambda, from compact support to all the lambda inside M of G. This finished the proof.